Today's speaker is Dr. Wang, who's the founder and CEO of Gaiamesh, a company that produces AI-based control algorithms that generate substantial energy savings by optimizing HVAC operations and managing user behavior. He holds a PhD in civil and environmental engineer from Stanford University, and undergraduate and graduate degrees from UC Berkeley and MIT. And prior to founding Gaiamesh, Ping worked in the R&D department at Walt Disney, focusing on BIM and the Internet of Things initiatives there. We have a big panel of discussants. Chad McKee, who is a senior lecturer and specialist in sustainable environmental design here. Hongshan Wu, who is assistant professor with an expertise in integrating advanced technologies into architectural design, particularly to enhance thermal comfort. Correct me if I'm wrong, Hongshan. And then Mark Tan, assistant professor specializing in structures and computational models. And the discussion will be moderated by myself and by Professor Wang.
Okay. Thank you so much, David, for the kind introduction, and thank you, Professor Wang, for inviting me to give this talk. So it's feels really good to be back in the kind of architecture department. I did my architecture degree at undergrad in Berkeley, and then my master's at MIT, actually under the tutelage of Professor Young-Ho Chang here. So it was really great to see you again. But then since then, I've moved a bit away from design and, keeping one foot, I think, always in the world of design, but then blending that as much as I can with a lot of the technical aspects around building energy efficiency and operations. So that's always something that I felt is really important to try to bring back into the fold into the architectural education. So I'm really, really thankful for this opportunity. So my talk today is titled Balancing Energy Efficiency and Resilience in a Shifting World. And what that means, I'll first go over kind of the problem statement, a proposed method, some example case study projects, and then looking forward what we aim to do in the future. So first, as David mentioned, talking about the magnitude of the problem. I think everyone has seen this graph in some form or another. This is the global carbon emissions curve, the total amount of emissions in terms of gigatons of CO2 per year, and also what is the effort that is needed to reduce that to meet our net zero emissions targets. So it looks really, really ambitious. And we did get a little blip there during COVID where actually the emissions went down, but now we're back up again, and it looks a little bit like Mission Impossible. But we have to do it. And what's the biggest component of this, right? I think all people have also heard the figure. I think around 42% of that emissions comes from the built environment. And if you break down the built environment part of that is the actual, what we call embodied carbon inside the building. So your building construction and the infrastructure, but the lion's share of that is really the building services. So around, these are approximate figures cited from the International Energy Association, but about 27% of the total global carbon emissions is from building services alone, right? So that's we have to deal with this if we are to solve this larger global problem. So more than a quarter. Now, another interesting challenge that is more and more apparent recently is that all this power demand from AI computing centers, it's actually doubling it's rising at the speed of it's doubling once every 2 months. So in the bottom you have essentially the y-axis is the amount of power that's consumed by these data centers, and on the x-axis is time. And you can see that pre-GPU computing during pre-2010, the computing power was doubling about once every 24 months. Once we had GPU computing and some of the earlier models, we started doubling at a speed of 3.4 months, once every 3.4 months, and now with large language models, we're going at once every 2 months. And you can see our friend Jensen there, he's constantly plugging these things in, right, and putting huge demand on the grid. And that's also counted into our building services part of the picture, right? So that 27% is getting bigger and bigger really fast. So on top of all this, right, then we have the increased carbon emissions leads to extreme weather events that then lead to more emissions to maintain those building services because they're now more energy intensive. So this is so I live and work in Shanghai, so I've been through a few of these interesting events. And so on the left-hand side, there's actually Shanghai in August 2022, when the temperatures reached an all-time high of 40.9 degrees, and then actually they shut off all the lights on the bund just to save energy because the demand exceeded the supply. Now, on the right-hand side, this is this year, just a couple months ago. On the 4th of August, we got close to that all-time high of 40.4 degrees. This time, we met the demand. Nothing was turned off, but that's because we built a huge amount of supply. Right? So we reached a record power demand of 40 gigawatts, which is more than the entire capacity of the Philippines. Right? So that's a ridiculous amount of power that is supplied there. So this shows how there's this vicious cycle, right, of increasing carbon emissions, increasing weather conditions, and then increasing power consumption, and then more emissions again. So how do we face this kind of problem? So that leads to the kind of question around my talk, right? So how to balance energy efficiency and resilience given these external forces? So resilience is essentially how highly available are your building services. You want to maximize the uptime of those services. And then energy efficiency is, doing more with less. So how do you use less, but then be more available? That seems like there's it's kind of a zero-sum game. But I think if we look closer at these buildings and look really closely at the data, we can find some pretty interesting opportunities. So this is so I think there are lots of terms around like resilience, reliability, robustness that get thrown around a lot in the literature. And I think it's interesting to use an analogy to describe the difference between those three. So this is actually outside my window in Shanghai, and we had the worst typhoon the city has seen in 75 years, like last month. Actually made me miss my flight to the US. And so my wife and I, we really like the trees outside our window, right? Because those trees provide us certain services. They provide us a view, and they provide us privacy, and they also provide us, to a certain extent, fresh air. So we were really worried that when the typhoon hit, and this is, it looked pretty scary at the time, that these trees would snap and we would lose all those services, and then our home would like not be as nice anymore. So it was interesting for me to think about these trees in terms of these three terms: reliability, robustness, and resilience, that often get confused. So reliability is kind of like what you think of as uptime, total percent uptime of a service, right? Is just a simple division problem. Robustness is more like how much force something can take before it fails. And resilience is how quickly it can recover. So in terms of the tree, the reliability is just the percent time that we have that service of the privacy and then the view. The robustness is how much wind force, for example, that tree can take before it snaps. And resilience is actually how quick that tree can grow back and the service can recover after there's this failure event. So here in this talk, I'm actually using resilience as the main kind of metric because it's to me, it's more of a human-centric metric that's really about minimizing the duration of impact to the occupant. So for example, like Bucky Fuller would design these very lightweight structures so that they could recover quickly instead of falling on you and crushing you, right? So they're much more resilient, maybe less robust. So that's, but ultimately, we as people, we don't really deal well with long failures, and if it's a long outage. But if it's short and it recovers quickly, it's more friendly to the user. So here I'm going to talk about a method, basically how to address this problem. And first, with a bit of an overview on, we're focusing, I talked about building services as a whole, but focusing on heating, cooling, and ventilation. So essentially HVAC, this HVAC services of building, which actually can be provided by your, what we all know as the HVAC mechanical systems, or by the building passive systems. So like to call those the passive versus the active systems of the building. So the building, so the heating and cooling and ventilation, these services comprise of on average, about 40% of building energy consumption. And in hot places like Shenzhen, Hong Kong, it can be anywhere between 50 to 70%. So it's a really big number. And I like this little illustration that shows how throughout the different centuries, there's been a changing balance between passive and active systems. So in the 19th century, it was much more passive. It was really thick walls, and you had your active systems with your fireplace, but that your walls would hold through the thermal mass, hold all of that heat inside and keep you warm. In the 20th century, we got into these buildings with a lot more active systems, a lot of ducts and wires and pipes that would consume energy and to maintain the service level of the building. And then now we're moving into kind of again into a more balanced kind of perspective on having much more. I guess here you can see that the passive systems are a bit thicker. There's more insulation and there's more advanced passive systems technology to enable us to have smaller active systems that use less energy. So there's this interesting dichotomy between these two systems as we develop our building technologies. So common active systems. Essentially, this is just an overview for maybe some members of the audience here are quite familiar with this, but this is for people who don't work with HVAC very much. On the active side, it's really made of three components, and generally these systems are made of a heating and cooling source, and then so that's where the cooling is kind of pumped into the building and the heat is pumped back out. There's the distribution system, which takes all the heating and cooling from the source and distributes it to your rooms. And then there's what we call terminal units, which are these little devices in the rooms that basically take the cooling or heating energy from your fluid and convert it into the air so that people can feel that comfort. And the common HVAC system types, there are generally two large types. There's what we call VRF, or variable refrigerant flow systems, and there's a central water-based system. So essentially one is using refrigerant and one is using water. And you can tell the difference if you're interested as an architect, you want to kind of understand which is which. The big machines look kind of similar, but usually it's in the pipes. The pipes look a bit different because the refrigerant-based systems have many smaller pipes that are copper because it's not at high pressure, whereas the water-based systems have these large, consolidated pipes. So that's just one quick way of understanding which is which. Overview of some of the common passive systems for heating, cooling, ventilation. You've got, of course, I think these probably you are all much more familiar with. Natural ventilations with cross ventilation, single-sided stack ventilation. You've got evaporative cooling, which could be water-based or it could be through, essentially wind blown through vegetation or trees that also has an evaporative effect. You have solar gain, so how to control the gain into your building through your shading devices, through your fenestration, and then finally thermal mass, that storing heat usually from solar, but could be from your HVAC system, and then so it's storing heat at certain times and releasing heat at other times. So it basically smooths out that temperature curve so that you have smaller peaks and smaller system sizing as a result. So all of these are deeper topics that I can go into, but today I'll just keep it light. And this is one of my favorite charts. I don't know if anyone seen the psychrometric chart before? Yeah, this is a great chart. So it's essentially temperature on this axis, and then humidity on this axis, and these curves are the relative humidity curves. So as the air warms up, it can hold more absolute humidity. And what's really interesting here are you first have this, essentially the blue is just data that is associated with whichever region the climate of that particular location. So I think this could be like Seattle or something. If you're in Hong Kong, the points will be much higher on the humidity and temperature area. So the blue is going to be scattered like way over here. And these boxes are essentially, the green is like the human comfort zone, right? So this means that any of these blue dots inside this green area, that means that those days you don't need to use any energy for your heating and cooling systems. So that's where you're good. And you can extend these boxes into using different strategies. So for example, if you used thermal mass-based cooling, you don't need to use energy in this larger box that is labeled thermal mass. If you use natural ventilation, you don't need to use any energy in this kind of pointy box here. So essentially using different passive system strategies allows you to completely avoid using energy or using your active systems within a larger range of outdoor temperature. So this is a really useful tool, I think, for architects and for engineers to understand what interventions can be used in different places and at different times. Here are some examples of architecture that I find interesting, especially in terms of passive and active systems design. Well, this is the Alhambra, and it's built so long ago that it doesn't really have any active systems, so it's purely passive. And it's in Granada, Spain. And what's really interesting about this building is that it's set back against the mountains, and it has an aquifer where the water runs from the mountains through the building in really intricately designed ways, and it flows down into the valley. So the whole building is designed around this flow of water from the mountains. And it really uses that water flow, right, essentially for sense of ceremony and ritual, but also for evaporative cooling, a very kind of engineering purpose, right? When the wind blows over these ponds, you can, just by looking at this picture, you can kind of feel how much cooler you are in the shade next to that pond than you would be outside in the kind of arid landscape, right? So it uses a combination of the evaporative cooling and all these multi-layered arch hallways to provide shading, and of course the heavy stone masonry to provide a lot of thermal mass for the building. Another interesting one, I mean, just as an aside, if you ever walked on the Great Wall of China, when you walk into those little turrets, right? And it's extremely cool in there. It's very hot and humid outside, but every time you walk into one of those turrets, you feel that thermal mass. It's very, very palpable and quite powerful. And so that's the kind of feeling that I would imagine you would get here. I've never been, but it's one of my favorite buildings. Another one is more on the modern side with a combination of active and passive systems, the Pompidou Center in Paris. And this one is it's quite a controversial building, right? So it has all of the systems exposed as a testament to the new architectural technology or the building technology at the time. And I would say that while it glorifies building systems, it does not make the best use of them. So because it's more like an expression of function and aesthetics, but the actual efficiency of the systems, if you look at the way that the glazing is oriented, if you look at the insulation of the building, it's all quite lacking, and the building actually uses quite a lot of energy. However, I think what's quite interesting about it is that it is built kind of for retrofit almost. At least the expression of the architecture is that you can come back, you can analyze this building, you can look for opportunities for improving the efficiency, and you can pretty easily do something about it. So I think that's its strength, that it is designed to be easily upgraded, and I think that's actually something that's quite important in today's world, because many buildings most of that energy waste is not from new buildings that have quite efficient systems, but is really from like 90% of that energy waste is coming from existing older buildings that's very hard to retrofit, right? So if we had a way to really easily go and upgrade the existing building stock without disrupting, the way people use the building, that's something that's quite important. So going back to how do we balance energy efficiency and resilience, right? So I think one of the opportunities here is to solve the problem with greater granularity of building operating data. So what I mean by granularity is, for example, if you take a building and take the example of a building electricity use. So if you have a whole building and it has 1 meter, right, you just know how much that entire building uses. that's very low granularity, because you can't do much with that data. You just know, okay, well, this building used, $10,000 last month. What can I do? But then if you start breaking it down into more and more finer grained kind of pockets of data, if you start measuring at the floor level, then you can say, oh, well, certain floors are wasting more than others. And why is that, right? You can start to investigate. And if you really start to break it down to every space, then you can start to see really, really interesting patterns and really a lot more kind of opportunities for improvement, for optimization, et cetera. So kind of the thesis here is that increased granularity of building data can reveal opportunities for improvement that weren't visible or are not currently possible to see. So, so this is the kind of proposed method for balancing resilience and energy efficiency using this granular data. And essentially, it comes in 4 steps. So first is to collect that data, right? So to understand what is actually going on in the building at a very fine-grained level. And then maybe, most of these buildings, the supplies, this kind of split between demand and supply. So you're understanding how people are using it. And the supply side, usually these buildings are, let's say it's maxed out in terms of the HVAC side. Step 2 is to say, can we reprogram this building based on that data? So kind of like programming in terms of space usage at the beginning of the architectural design process, but more like, can we reprogram it based on how we understand people are using it, how we're actually using it, right? So that's kind of a very interesting new step that we can bring into the building management process. Once we reprogram it, we can actually find, certain spaces, maybe they're not being used, maybe certain spaces are really active, right? And how do we then rebalance against that new program? So use different passive and active building technologies to try to get everything to fit within the new set of requirements. And then finally, when there are these like extreme events, like there's a heat wave in Shanghai again, then how do we, with that excess capacity that we've gained from the rebalancing process, how do we redistribute that, right, to those spaces that are most sensitive and most highly affected in those extreme events? So this is how we can essentially reduce the energy consumption, create excess capacity, and then redistribute in terms of when in extreme cases. And that is that balance. So going to step 1, collecting granular operating data. This is a office building in Shanghai. It's with one of our customers, and we took some very interesting measurements here on the color scale is essentially the temperature, right? So from 30 to 18 degrees, 30 is red, 18 is blue. Outside temperature, indoor temperature, color coded the same way. The dots are occupancy, like how often people are using the spaces from 0 to 100%. And we use these little sensors that we produce. And you can see that if you play this over time, and we have a much longer kind of segment of this, but you can start to see how people populate the building at different times of day, and you can discover how the temperature changes inside and outside. And you can kind of discover all kinds of interesting behaviors that you weren't able to see before. I'll highlight a few, and then in the next couple slides. But this is essentially that granularity that we're talking about, right? And the new kind of visibility we can bring that helps to be this first step of starting to re-evaluate how our buildings are actually used and how to make them more efficient within those patterns. So if we go to the next slide, so you can see that, it's Friday evening at 8 p.m. and some people have left their aircon on to work, right, after work, and that's quite interesting. Those are already opportunities for saving energy. You can see that there's at 1 a.m. there's some really heavy activity in the storage room after hours, and why are the building is being used in ways that we maybe didn't expect. Also, on a Sunday, there's an explosion of activity, right? And then these same 2 rooms are also always, for some reason, very cold. So how do we start to summarize all of this information? I guess we have all of it, you can play it over time, but how do you make sense out of it? So that's kind of the second step, which is where we start to reprogram. We reprogram the building for resilience. And here, what we can do is, first, I think a lot of buildings actually don't have like actual, temperature requirements that are set per space, per building, or per type of space, right? So you can actually go through and just quite simply say, okay, for each of your types of spaces, like small meeting rooms, large meeting rooms, and you can take, for example, a survey of the occupants, or just come up with this directly from building management. What's the acceptable range? Like maybe these meeting rooms are kind of 20 to 26, that's okay. Public areas, I don't mind as much, I can keep it a bit broader. Labs, they're very sensitive, and my experiments can be spoiled by a difference in temperature, so let's keep that within a 1 degree range. You can think about this also in terms of robustness, right? At what outdoor temperature can I guarantee these indoor levels? And then finally, what's the recovery time? Right? When there's an extreme event, how fast do each of these spaces need to recover? If it's a classroom and there's a big session happening, maybe 30 minutes is too long, and students start to lose attention. So let's get that back within 15 minutes, right? So those are interesting requirements we can set for the different kinds of spaces. And then you can look at the occupancy data in terms of those different kinds of spaces and see, well, which kinds of spaces are being used more over time. So here we can see that the students use the small meeting rooms, across the entire day, right? 24 hours they're studying, and they're using these study group rooms. Maybe the other rooms are used more normally, and the labs just require this kind of 24/7 attention. So you start to create like a new box of requirements around your space. And if you look even closer, like if you look closer into, for example, the public rooms, then you can say, okay, well, 6th floor, 5th floor, heavily used public spaces. But in the other spaces, for example, 1st floor, 2nd floor, before noon, nobody's even there. Why don't we don't even need to, we can just close that space off. We don't need to condition it. We don't need to patrol it. That creates a kind of new, interesting bounding box for how the building is used and how people live in it. So that's kind of what we mean by reprogramming for resilience. Because by doing that, you're exposing, or you're releasing extra capacity. So step 3 is rebalancing, and this is where it gets more interesting in terms of interventions. So this is data collection, analysis, and now we're actually going to propose some interventions that create some extra excess in the capacity of the building that increases the resilience of that program. So we can first look at, okay, well, with these new requirements that you just set for yourselves, how are the spaces performing? Right. So some of the spaces we can see, okay, well, actually they're even against the new requirements, they're maybe too hot when it's occupied, or some spaces they're within the bounds, but maybe they're spending too much energy. Right. So there's a whole range of kind of findings you can see once you set this new boundary against the data. And what we can do at this point is looking at that the current behavior of the building. For example, we can even look at the Knowles building and see what's the temperature, humidity, CO2 over time in different spaces, and actually propose some lightweight retrofits to the passive system design. I'm not sure how practical that is here because I haven't studied this building in that much detail. But you can propose, for example, redoing the fenestration to enable more natural ventilation where it's appropriate. You can propose to you can use some of the water systems, for example, or maybe even the condensate of the HVAC to enable evaporative cooling in spaces without using extra energy. You can add light shelves. You can add a fish tank for thermal mass, as long as the fish don't mind a little bit of temperature swing, right? And you can do all that with kind of using this psychrometric chart as a guide. So once we've been able to implement a certain level of passive interventions that building, then you can go again, and it always goes passive first, then active second, right? Because the active is the energy spending part. And what we can do here is essentially apply surgical control retrofits to actively balance supply and demand, given the new bounding box you set for yourself and the new passive elements that have been placed in the building. So we actually usually do this backwards, from the terminal units back to the heating and cooling source. First, on the terminal unit side, for example, if each of these boxes is one point in time in one room, we can say, okay, well, some spaces, it's too cold, when there's people in there, or some spaces there's no one in there and it's still cooling. So how do we make it so that when there's people in there, the temperature is just right, and then when there's no one there, we kick it up 2 degrees, right? That's what's called a setback temperature, and this is what we can achieve if we can start to control every individual unit and using also the fine-grained data that we collected in step 1. On the distribution side, what we can do is actually, while maintaining the balance of each space, we can actually optimize the way that the water flows through all the pipes. Because what you'll find oftentimes, and I'm sure with these systems in this room as well, is that the water is flowing actually way too fast in these pipes, and we're not using all of the cooling in that water before it goes back, and usually goes back too cold to the central plant. So what we can do is actually, by doing this fine-grained control, we can slow down the water flow and pull more cooling out of per cubic meter of water, so that the water goes back warm and we get as much cooling into that room as possible. And there's much less flow in the pipes, which saves money on the pumping side. And then on the heating and cooling source side, again, it's balancing supply and demand. So usually these systems are controlled manually. So people turn them on at 8 a.m. every day to get it to 9 a.m. At 22 degrees Celsius, right? But it's very manual. So as the temperature changes across the season, you can, there's this kind of predictable temperature curve that, as it drops when you turn on the system, so you can predict when's the optimal time to turn the system on. So you just meet the demand when it's needed, using control at the source. So again, each one of these, it's a whole kind of in-depth technical discussion. I'm not going to go too deep in it, but happy to talk about it afterwards if anyone is interested. But that's on the active side. How do we essentially balance out supply and demand on an active side and release this extra capacity? And then finally, this is kind of newer research, but how do we start to redistribute that extra capacity in these extreme events? And what we're looking at now is, okay, well, if there's another high temperature event, can we then do a prioritized predictive kind of buffer allocation or allocation of that excess capacity based on the types of spaces? So you saw how the different spaces had different resilience requirements, right? So the labs wanted to get back within that temperature and within their temperature band within 5 minutes. So all of that excess capacity first goes to the labs so that the labs can cool down well before that resilience kind of boundary. Second, then the classrooms, because the students, we want to keep the students happy. So we predict that temperature curve and we make sure that the classrooms get back into the range on time. And then finally, the typical rooms. So it's a way to redistribute the excess capacity that we created in a very intelligent way. In terms of, we've applied some of these methods to a number of case studies. So the first one is NYU Shanghai. This is the new campus that they built in Qiantan. It's around 110,000 square meters, and it's interesting building design. It looks like a courtyard house, right? So an entire city block that's 12 stories and with a central courtyard in the middle, and designed by KPF. So for us, the challenge was the annual energy cost here was 18 million RMB. And actually the heating and cooling part of that was 61%. So 11.2 million RMB of that was heating and cooling costs. They had about 2,000 different aircon devices distributed over thousands of rooms. So we deployed a couple thousand of our sensors and controllers to manage all of that. And the question is, it also is an operating university, right? So we didn't come in when it was being built. We came in when the students already started classes. So how do you save energy for a campus with thousands of these devices with zero disruption to operations? That was our main goal. So we basically used our system, which is this. So we did most of our intervention here is on the active side. The passive is kind of a new exploration for us. I think much more in the spirit of kind of architectural design. What our company does is mainly on the control side. So we deployed this wireless mesh technology, which allows all of these devices to link together into this wireless network, communications network, and it supports a large-scale plug-and-play installation, and you can see how it's really easy to go and replace one of these devices on the wall. And then that control logic for supply and demand balancing is actually optimized in the cloud, and then based on the data that we collect, and then actually gets downloaded into the mesh and it runs in these kind of in-mesh control loops between the devices, kind of these wireless control loops. So it's a distributed wireless control, which is quite interesting, because then even if your cloud has a problem, or if your internet goes down, everything, the AI that's been optimized in the cloud is running kind of all around you in these wireless networks. And then there's this management platform that allows the school to basically keep tabs on everything, right, and quantify how much they're saving. And so this is some of the initial results. We're only in phase 1 right now, but essentially we saved about 17.2% of their HVAC with a cost savings of 900,000 RMB, and that's about a 2.5-year payback period. So just from a school management perspective, obviously you want to understand how financially this makes sense. And of course, we're moving into phase 2, which is actually really a lot of interesting new applications can be deployed, since we've collected all of this data, and we can actually see that, for example, the user behavior on the set point side. You can see that not only what temperatures is in each space, what do people want, right? What are people setting on each of their panels? And you can see most people, they feel like they're too hot, so they like to set the temperature way too low. No one really wants to be at 18 degrees, but everyone, when they're in a panic, will hit that button on the thermostat and go down as low as you can go. But this also means that it actually probably means that the system is unbalanced, right? Because it's not able to meet the user demand when they're asking for it. But you can see that there's essentially a large room for savings as well. So if people set more reasonable set points, you can actually, if you stay in the suggested level, right, you can make the whole system more resilient just by making people more comfortable. And that's something I'm always interested to learn more about in Hong Kong, where it's always uncomfortably cold here for me. And that seems like the cultural norm. So I'm really curious to understand the drivers behind that. So there's occupancy-based control, which, if there's people in the room, you can see that we change the set point down. If there's someone leaves the space, then the temperature jumps up versus the baseline. And finally, there's that water flow optimization, where you can actually see here, this is the kind of how the water flow, or the valve opens and closes in the baseline condition. The temperature is held steady, but then here we're actually opening it much less, but at a higher frequency, right? And you can keep the temperature just as steady, but you're using 30% less flow, and you're saving about 50% pumping energy savings. So we think that by deploying these new methods across the entire campus, we can reduce up to 30% with less than 2-year payback. We've started some research collaboration with Nanfang Keji Daxue, or SUS Tech in Shenzhen, and this is just kind of early studies as well, but this is from the Liang Lab at SUS Tech, and essentially we can see that in these more southern climates, there's essentially a larger potential because, well, you can see actually the occupied periods here are quite large. The students are working really hard in the lab. And then during those times when they're working really hard, actually the temperature is quite low, way below the school recommended temperature of 26. So ideally, you would have the temperature at 26 when there's somebody in the space, and it's at 28 kickback when there's nobody in the space. And this red line is the actual, right? So there's all the space between the idealized and the actual. That's the potential for savings, right? And that's about 35%. Whether we can actually control on this very orthogonal line, that's not possible. But that's the room that's available there. So looking forward, just to summarize some of the main points of the talk. Right? So first, building operations, they consume about 27% of global carbon emissions, and the power demand from AI computing is doubling every 2 months, so making that 27% much larger, much faster. Now, we do have this new opportunity where we're seeing a lot. We're now able to collect and understand a lot in much greater detail about how our buildings are actually being used by the occupants, right? And we think that this increased granularity of the building data can yield a large amount of energy savings. It can start to balance out some of these carbon emissions. Now, we've proposed a framework of essentially granular, using that data in a four-step process to collect the data, to balance the resource usage, and to allocate the buffers to achieve both energy efficiency and increased resilience. And we've applied that method we've applied that framework essentially on building active and passive systems for heating, cooling, and ventilation systems. And then we've tested the method at full scale on university campus, active systems only. The passive systems we're really kind of interested to explore more about, and then the preliminary results, about 70% savings, and while also increasing the system capacity, and then also with no disruption to operations, right? So students keep going to class. And future work, I think why I think this is such a meaningful topic is that with the new data and the new AI tools that are available, how much energy efficiency is achievable by combining these two new methods, right? And what % of those savings are going to be active versus passive? I think that's a really, really interesting question for us, right? And then also, what is the optimal level of granularity for that data? Because you can keep collecting as detailed as you want, but there's a diminishing returns in terms of cost at some point. But overall, looking at this carbon curve, can we use these new tools and new data to actually help us drive this curve down instead of bringing it up? And I think we're quite optimistic that AI, and combining AI with this new data, we can save more energy than it uses and help us achieve our net zero targets. So that's the end of my talk. So thank you, everybody.